Hi, on to chapter 2, I guess. So let's see what we got here. Okay, let's go back a few years. Centuries, actually, I suppose. Science has always been the way that we've always learned about things. You have your scientific method where you observe the world around you, and then you come up with some sort of an explanation as to why the things happen the way they do. And so you come up with a hypothesis, you develop that further, and you come up with a theory. Okay? For example, if I have a pen, and I notice that every single time I drop this pen, it always seems to just go down and hit the desk. All right, and so what I do is I come up with some sort of an explanation for why that might be. And so my theory for why the pen always seems to hit the desk, I'm going to call gravity. That's going to be my theory. Theories are tools. They're kind of like a socket wrench. What would you use a socket wrench for? Well, if you had a lot of bolts and nuts around your house, the socket wrench comes in kind of handy. Well, theories are kind of the same way. They're tools to explain the world around you. For a theory to be useful, it has to make predictions, and those predictions have to come true. If I have a theory that doesn't explain anything, then it's kind of like having a socket wrench that kind of sits around the house that doesn't fit anything in your house. If it doesn't fit any nuts or bolts in your house, you could probably throw that socket wrench away and just get on with your life and it'd be just fine, right? Well, that's kind of the way theories are. So we come up with these theories, we try to explain what's going on. The next thing we do is we test to see if those theories happen to be true. So my little theory here, which I'm going to call gravity, says that when I drop this pen, it ought to go down and not up. So here we go. There we go. All right. And I can keep dropping this pen over and over and over and over again. And every single time I do, it goes down. It doesn't go up. So if I have a theory that I test over and over and over again, and it just always seems to hold, then it graduates into a scientific law. And that would be called the law of gravity, which you probably have heard of before. And yes, I didn't come up with it. Well, that's the way we do things these days. But science wasn't always the only game in town. Back in the age of the Greek philosophers, what people thought is if I had any problem at all, I could sit there and I could just think about it. And if I think and think and think, I could solve any problem just simply by thinking about it. These days we do experimentation. That's why there's a lab component to your course. I don't know how you can teach a science course without a lab, but because it's such an integral part, but I guess it's possible. But back in the age of the philosophers, they didn't do any experimenting, they just sat around and thought. So here is a philosopher named Democritus, and he's sitting there thinking, as philosophers tended to do. And he said, you know what, I could take a pen. I probably didn't have a pen, but just, it's kind of, bear with me for the purpose of the illustration here. I could cut this pen in half, and then I could take that half, and I could cut that in half again. And I could take that half, and I could cut that in half again. And he said, eventually I'd get down to a piece of pen that is so small I couldn't cut it in half with my knife again. And if I ever get to that point, that must be the smallest piece of matter that can exist. And he called that an atomos, which in Latin or Greek actually means indivisible. Well, was Democritus right? Is there a smallest piece of matter that you can cut down to and not get anything any smaller? Well, it turns out, yes, he was. Philosophers weren't stupid. They knew some things. It's just that Democritus really probably never had a clue how far down you could go to get there. So let's fast forward a few centuries, and let's go to the 1800s. So early 1800s, 1812, somewhere in that range, 35, something like that. Here comes a fellow by the name of John Dalton. Okay, and John Dalton proposed his atomic theory. Okay, these are the postulates of atomic theory, and you will find them in your book on pages 68 and 69. And it's, half of this page and half of another page. So what I'm going to do is I'm going to kind of condense things down. You can read those over if you want to, but I'm going to give you the high points here. All right, so what did Dalton's atomic theory say? Well, Dalton said that elements consist of tiny particles called atoms which retain their identity in a chemical reaction. In a compound, atoms of two or more elements are combined in a fixed ratio of small whole numbers. In other words, 1 to 1, 1 to 2, 3 to 2, so on and so on and so forth. Okay? Now, what experimental evidence tends to bear out Dalton's atomic theory? Well, I know that I can take hydrogen gas and I can react that with oxygen gas. And when I do that, the hydrogen burns and I get a whole lot of heat out of this and I get water. Well, it turns out that I can go the other way here. I can take water and I can break that back down, because remember, compounds can be broken down by chemical means. Easiest way to do this would probably be electrolysis, which just means running electricity through it. And when I run electricity through my water, what I get is I get hydrogen and I get oxygen. But I always get hydrogen and I always get oxygen. I don't ever get beryllium and carbon or iron and nickel. It's always hydrogen and oxygen. So what does that tell me? Well, that tells me that when I combine the two elements together here, this hydrogen and oxygen, the hydrogen still must be hydrogen when I form the water, and the oxygen must still be oxygen. Because when I break the water back apart, I always get hydrogen, I always get oxygen. All right, so therefore the elements maintain their identity in a chemical reaction. Make sense? All right. Well, do you remember we talked about how compounds are always found in fixed mass percents? Remember we said water was always roughly 89% by mass oxygen and 11% by mass hydrogen. Why is that? Well, it's that way because in a water molecule, you always find 2 atoms of hydrogen and 1 atom of oxygen bonded together. And that's what makes that water. If I had a water molecule that had 2 hydrogen atoms and 2 oxygen atoms, it's not water, it's something else. It's a different compound. And that would be called hydrogen peroxide. But all hydrogen peroxides have 2 hydrogens and 2 oxygens bonded together. All right? This is called the law of definite proportions. And essentially what it comes down to is the reason that compounds have fixed mass percents is because they always have fixed atom percents. Since water is always 2 atoms of hydrogen and 1 atom of oxygen, that's what makes it water, then the mass percents are going to be the same as well. And so that's another thing that Dalton's theory kind of explains. All right, so Dalton's theory explains a lot. It still explains a lot today. And in fact, here in the 2000s, we still keep it around. It's a very useful theory. I'm a chemist, so I'm kind of biased here, but probably of the early 1800s, 1800 to 1850, I think you could make a case for it being probably the most important scientific discovery of the early 1800s. 1850 to 1900 and 1900 on, well, we can talk about that. But that's just my opinion. It's not in the book or anything. Okay? All right, well, is it possible to take an atom and actually break it down into smaller particles? Well, it turns out that if you use extraordinary means, you actually can. So there are what we call subatomic particles. Now, there's a whole host of these, and we could turn this into a class in particle physics, and we could talk about mu mesons and pi mesons and neutrinos and all sorts of exotic subatomic particles. But really what we need to know here is just the big 3. All right, so let's talk about those. All right, the first type of particle you run into in an atom is something called a proton, and that's abbreviated like this, as with a P with a little plus. If I took a stream of protons and I passed them between 2 charged plates, what would happen is the path of them would actually bend down like this. All right. What can I infer about the charge of a proton? Well, if the path bends down, remember opposite charges attract and like charges repel. So notice it's being attracted by the negative plate, so that means it must be what charge? Positively charged. All right. Notice that it's being repelled, being pushed down by the positive plate, because like charges repel. And so therefore that's experimental evidence that it's got a positive charge. All right, how much charge? Well, I could give you the charge in coulombs, and it's a little tiny number in scientific notation. But again, nobody likes those little tiny numbers in scientific notation. So we're going to talk about relative charge here. Okay, well, relative means compared to, so relative to what? Well, I guess another proton, because that's all we've got. So this proton has just as much charge as that proton. So we're going to say they have a relative charge here of +1. Okay, see, we're making the math easy for you here. All right, mass-wise, I could give you the mass of a proton in kilograms. But again, really tiny number, somewhere on the order like, 1 times 10 to the minus 23rd or something like that of a gram. Something along those lines. It's really, really tiny. And we don't want periodic tables with scientific notation in. So we're going to talk about relative mass here. So again, compared to what? Well, another proton. So this proton weighs just as much as that proton, so we say it has a relative mass of 1 AMU. And AMU stands for atomic mass units. All right, so protons have a relative mass of 1 AMU, and they have a relative charge of +1. All the protons are found together, bundled together in the center of the nucleus, center of the atom, and that's something called the nucleus. Okay? All right, well, the second particle that you run into in an atom is something called the neutron. Neutrons are actually fairly recent innovations. They were discovered in 1935, so, fairly recent there. Neutrons are abbreviated by this little N with the O here. All right, turns out that neutrons weigh pretty much the same as a proton. Not exactly, it's complicated, but pretty much the same. So if it weighs the same, it's got a mass of 1 AMU as well. If I took a stream of neutrons and passed them between two charged plates, they'll go straight through without bending at all. What can I infer about the charge of a neutron? Well, it must be neutral, see? And so therefore neutrons have a relative charge of 0. All right, neutrons are also found in the center of the atom, bundled together with the protons in something called the nucleus. So what do neutrons do? Well, think about it. You've got these little protons and they're all positively charged, and you're cramming them together. Do you think they're going to stay together? Well, no, because like charges repel, right? So why doesn't that nucleus fly apart? Well, two reasons why. The first reason is something called a strong nuclear charge, which is actually a force that applies at very, very small distances. And so if you push your protons together, they will fight each other, that electrostatic charge, repulsion. But if you get them too close together, then what happens is that strong nuclear force takes over and that binds them together. All right, the second thing, which is kind of important to you here, is the number of neutrons. Neutrons are kind of like the glue that kind of holds that nucleus together. Generally speaking, for a lighter nucleus, you need about 1 neutron per 1 proton to make a nice stable nucleus. The bigger the nucleus, the more glue you need, and so therefore it's roughly 1.3 to 1.4 neutrons for every proton for your heavier nuclei. It's not twice as many. It never goes up to twice as many, but it's significantly more than 1 to 1. All right, because you just need more there to kind of hold that thing together. And that's what the neutrons do, is they help stabilize the nucleus. For most elements, there's one particular combination of protons to neutrons that is really stable. When we say stable, we mean low in energy. All right, if you don't have enough neutrons, or if you have too many, that makes that nucleus unstable or high in energy. And so that nucleus is going to try to get rid of that excess energy somehow. So how does a nucleus get rid of its excess energy? Well, that's radioactivity, and that's why some things are radioactive and some things aren't. Next year, we'll talk about it. When we get to the end of the course, we'll talk about it in Chem 2, radioactivity. But that's what it comes down to, is it doesn't have the proper number of neutrons. So yeah, neutrons are kind of important, even though they don't really add any charge or anything like that. Okay? The third particle you run into is something called an electron, and that's abbreviated with this little e with the minus here. Well, it turns out electrons are much, much, much less massive than a proton or a neutron. It takes 1,872 electrons just to equal the mass of 1 proton. All right, so relative mass there, 0.0005. So hardly any weight at all. If I took a stream of electrons and passed it between my charge plates, they'll actually bend up like this. Okay, why? Well, from that we can infer that the charge of an electron is negative because they're being attracted to the positive plate as they pass through. They're also being repelled by the negative plate, see, as they pass through, and that's what causes the path to bend. Now again, we could give you the charge of the electron in coulombs, which is your SI unit, but again, really tiny number. Turns out that an electron has just as much charge as a proton, it's just opposite in sign. And so therefore the relative charge on an electron is -1. All right. By the way, this is actually how they tell if subatomic particles in an accelerator, if they have a charge or not. They pass them through a magnetic field, and if the path bends, you know it's got a charge. And what they can do is they can look at how tightly that bend is, how much curl is there, and then what they can do from that is they can infer the mass to charge ratio. In other words, heavier things won't be able to be bent as much, lighter particles will bend easier, and then the more charge you have, the tighter the curl. If they just go straight through, then there's no charge. And so, yeah, that's actually how they do that, is they look at that, the bend of the pathway in a magnetic field. It's like looking at the tire tracks on a road and realizing a car must have been there. You realize it from the tire tracks. Kind of the same way here, sort of. All right. Electrons are not found inside the nucleus with your protons and neutrons, but they're actually found outside the nucleus in an electron cloud. All right. So put that all together. This is what an atom looks like. You've got your protons and neutrons here in roughly equal amounts. This is not drawn to scale in the center. And the electrons are out here somewhere in this region of space called the electron cloud. 99% of the mass is concentrated here in the nucleus. 99% of the space taken up is actually by the electrons. Now, you'll notice I didn't draw little tiny balls going in a circular orbit around the nucleus here. Why did I not do that? Well, I didn't do that because that's not how an atom looks. Can I prove it? Yeah, I can prove it. You can use plain old simple 1700 Newtonian physics to prove an atom can't look that way. The best you can do is say the electrons are out there somewhere in an electron cloud. Now, can I do slightly better than that? Yes, I can. Okay, and we'll talk about it in a later chapter. But for now, that's what an atom looks like. Remember we talked about the periodic table. We said the periodic table is your friend. All right, so if you look at a periodic table, what you will see is you will see the symbol for the element, but you'll see two numbers there. You'll see a whole number there, and you'll see a number with a decimal. Right? So let's look at the whole number first and see what that's all about. The whole number that you see there is something called the atomic number. Okay? And the atomic number tells you the number of protons in the nucleus of an atom. What makes that element is the number of protons. That's the important thing. I can have two helium atoms that have different numbers of neutrons. I can have two helium atoms that have different numbers of electrons, but I can never have two helium atoms that have different number of protons, because helium has an atomic number of 2, which means it has 2 protons. All helium atoms have 2 protons. If you find a helium atom with 3 protons, it's lithium. But all lithium atoms have 3 protons, and so on and so on and so forth. So it's the protons is what makes an element, and that's what the atomic number tells you. Okay, well, if you apply something called the principle of neutrality, then that tells you something even more. So what does the principle of neutrality say? Well, the principle of neutrality says all things being equal, atoms and molecules prefer to be electrically neutral. Principle of neutrality. All right. Why is that anyway? Well, let me let you in on a little preview here. Why is there such a thing as chemistry? How come when I take two things and put them together, they react? Sometimes they'll react, sometimes they won't react. But what is the driving force behind things reacting in the first place? Well, it's this general principle. You can call this Anderson's principle if you want to. You don't have to, but you could. All right. And Anderson's principle says, all things being equal, atoms and molecules prefer to be in the lowest energy state possible. If I have an atom or a molecule and it has this much energy, it wants to have this much energy. It wants to be down here, likes to stay down here. All right. Well, what if it has this much energy? Well, what it will do is it will try to find a way to get back down to here if it can. And that's why chemical reactions take place. How come when I mix beaker A and B together, sometimes it does nothing, and when I mix two more beakers together, it turns green and then fizzes, or explodes in my face, whatever. Why? Well, because my reactants, or what I'm reacting, have this much energy, and then what I'm producing has this much energy. That's the driving force. Now, what does that have to do with the principle of neutrality? Well, the principle of neutrality is kind of a corollary, I guess, of that general principle, Anderson's principle there. Because if something is electrically neutral, it's lower in energy than if it has a charge. So the principle of neutrality is really just saying, all things being equal, atoms and molecules prefer to be in the lowest energy state possible, or electrically neutral. That's really all it is. Okay? So if we know that, I know that my protons have a charge of +1. What's the only other particle in an atom that has a charge? Well, that would be the electron, right? What charge does it have? Well, it's -1. So therefore, the atomic number not only tells you the protons in an element, it also tells you the number of electrons in a neutral atom of that element as well, which is the way you're going to find it most of the time. Make sense? Okay. Well, what about that other number down there, the one that's a decimal? Well, the one that's a decimal is closely related to something called the mass number. Not exactly the same, we're going to talk about it in a minute, but the mass number. Okay, so take that number for now, for the next 10 minutes or so. Take that number, round that up or round that down. Okay, and we'll explain why here in a few minutes. All right, and what you get is you get something called the mass number. And the mass number is kind of a measure of how much does it weigh. So atomic number tells me the number of protons, the mass number tells me the weight. Okay, well, what do I have in an atom that weighs something? Well, I got protons which weigh 1, I got neutrons which weigh 1, and I got electrons which weigh 0.0005. Well, what's the largest atom you can find in a periodic table? Well, that would be element number 118, which has 118 protons and 118 electrons. Remember, it takes 1,872 electrons to equal the mass of one proton. The largest atom that you could possibly make at this point has 118 electrons. Is 118 anywhere close to 1,872? No, not even close. So for practical intents and purposes, can I ignore the mass of the electrons in an atom and get away with it 99.9% of the time? Yes, I can. Okay. Well, protons weigh 1, neutrons weigh 1. Boy, that makes it easy. So the mass number here is going to be equal to the number of protons plus the number of neutrons. But see, if they both weigh 1, add them together and that's your mass number. All right. Now, I can have atoms of the same element that differ in mass number, that weigh different amounts. But I can't have atoms of the same element that differ in atomic number, because remember, the number of protons are what make the element the element. All right. So, for example, there is a carbon atom out there that weighs 12. In fact, about 98% of them actually weigh 12. Most of them do. All right, what's the atomic number for a carbon atom that weighs 12? Well, 6. That's the atomic number in the periodic table. What's the mass number? Well, I told you it was 12. Okay, so how many protons does a carbon atom have that weighs 12? Well, 6, because that's the atomic number. How many electrons do I have in a neutral carbon-12 atom? Well, if I got 6 pluses, I also have 6 minuses. So I have 6 electrons. How many neutrons do I have in a carbon-12 atom? Well, I know the whole thing weighs 12, and I know 6 of those are protons. So how many neutrons should I have? Well, 12 minus 6, the rest of them have to be neutrons, and so therefore I have 6 neutrons. So I have 6 protons and 6 neutrons in the nucleus bundled together, and then 6 electrons around the outside. All right. This is another way to write that. This is called the nuclear symbol. Writing it this way comes in handy sometimes when you're dealing with nuclear reactions. But we're here, so let's just go ahead and cover it and get it taken care of. So how do you write a nuclear symbol? Well, you put the symbol for the element here. Down here at the lower left, you put the atomic number. So that's a 6 here. Sometimes they'll just leave this off because you know it's carbon, so you know it's got to be 6. But formally, you put the 6 here. And then up at the top left here, you put the mass number, how much it weighs. So this would be a second way to write, hey, a carbon atom that weighs 12. And that's called the nuclear symbol. Okay? Well, it turns out that roughly 1.1% of your carbon atoms actually weigh 13. So what is the atomic number of a carbon atom that weighs 13? Well, 6. It's carbon. What's the mass number? 13. How many protons do I have in a carbon atom that weighs 13? Well, 6, because that's the atomic number. How many electrons in a neutral carbon-13 atom? Well, 6. If I have 6 pluses, I need 6 minuses. Okay. How many neutrons? Well, the mass number tells me I have 13 protons and neutrons. 6 of those are protons, so you subtract off the atomic number, basically. How many neutrons do I have? Well, I've got 7. All right, so how would I write a carbon atom that weighs 13? Well, 6 is the atomic number. There's your symbol. And then the mass number is 13. And that's how you differentiate between these two. Well, if you're doing the math here, you'll realize there's still about 0.9% of atoms left over. So what are they? Well, those are carbon atoms that weigh 14. What do we use carbon-14 for? Well, it's actually radioactive dating, you know, when you're dealing with artifacts and things like that. So that's, again, a whole other subject, I guess. But yeah, that's this little guy right here. What's the atomic number of a carbon atom that weighs 14? 6. That's what makes it carbon. Mass number 14. How many protons? 6. Atomic number. How many electrons in a neutral carbon-14 atom? 6. 6 pluses, 6 minuses. How many neutrons? 14 minus 6. There are 8 neutrons in a carbon atom that weighs 14. And this is how you would write the symbol for that to differentiate it between these other 3. Make sense? Well, what's the difference between these 3 carbon atoms? Are they chemically different? No, they're carbon. They look like carbon, act like carbon. They're just carbon. Well, why come one of them weighs more than the other? Well, it's the number. Is it the number of protons? No, not the number of electrons. It's the number of neutrons, and that's what those atoms have. Is they have different numbers of neutrons, but it still makes them carbon because they have 6 protons. Carbon-12, carbon-13, carbon-14 are referred to as isotopes of carbon. That's what an isotope is. All right. Generally speaking, what you'll find is generally speaking, you'll find one particular proton to neutron ratio that's really stable. All right. And most of the atoms are kind of like that. All right. But you'll find a few isotopes that have too many or too few neutrons. Those are found in lower abundance. And generally, they tend to be radioactive because they don't have the proper proton to neutron ratio. All right, and so for a lot of elements, you have one that's fairly high percentage and trace amounts of the others. All right, but yeah, they're all isotopes of carbon, and they're atoms of the same element that weigh different amounts, and it comes down to the number of neutrons. All right, if I gave you the atomic number and the atomic mass, could you tell me how many protons, neutrons, and electrons are in an atom of that element? Well, I've got a carbon atom here that weighs 12 and a carbon atom here that weighs 13. Well, 13 what? 13 grams? If I put it on the scale, is it going to weigh 13 grams? No, not going to weigh 13 grams. It weighs 13 AMU. Well, what's AMU? Well, that's an atomic mass unit. Well, what's an atomic mass unit? I don't really have a scale that weighs those things. Well, if you'll look at the periodic table again, we said that protons weigh 1 and neutrons weigh 1, but look at some of these masses in the periodic table. Are they even? They should be a whole number, right? Protons weigh 1, neutrons weigh 1. A lot of them are very close to a whole number. You can round up or round down, and you can get a nice whole number there. But some of them aren't. Look at chlorine, 35.45. That's somewhere in between, right? So where'd the 0.45 come from? Is that the electrons? Well, no, the electrons don't weigh hardly anything, so it can't be the electrons. So why do I have decimals there? Well, the number you're looking at there is really not the mass number. It's closely related to it, but it's not. It's something called the atomic mass. All right, so what is the atomic mass? Well, the atomic mass gives the relative mass of an atom. So I guess the question would be relative to what? If you're going to compare the masses of the atoms in the periodic table, which one would you choose to compare to? Well, the most common answer there would be hydrogen, because it's the lightest one, right? So if I call hydrogen 1, then everything else is greater than 1, and I don't have to deal with fractions. Do we like fractions? Nobody likes fractions, right? Okay, so that way we don't have to deal with fractions. And that makes a lot of sense, except that it's wrong. All right? The atomic mass is based on something called the carbon-12 scale. In other words, the most common isotope of carbon is assigned a mass of exactly 12.00000 out to infinity AMU. Okay, well, two questions here. Number one, why carbon? Number two, why 12, right? Well, the reason we use carbon instead of hydrogen is carbon's a solid. It's pretty easily found. It's pretty cheap. Hydrogen's a gas. It's flammable. You ever seen a picture of the Hindenburg? That's why we don't fill blimps with hydrogen anymore. And, you put it on a scale, it doesn't sit still. Hydrogen's so light, it will actually escape Earth's gravitational pull. Earth's gravity is not strong enough to hold hydrogen. So unless it reacts with something on the way up, it's gone. Most of the hydrogen is tied up in the Earth's crust and in water here on Earth. So it's a little difficult to deal with. So we chose something like carbon instead. All right, why 12? Why not call carbon 1? Well, if we call carbon 1, everything lighter than carbon would have a fractional value, and we don't like that. Okay, it turns out that a hydrogen atom weighs about 1/12 that of a carbon atom. So if we call carbon 12, then that makes hydrogen 1, and all of a sudden no fractions, which is kind of nice. And so that's why. All right? Well, once you know that, now you can start comparing masses of atoms to atoms, masses of atoms with other atoms. So, for example, atomic mass of boron is 10.81 AMU, calcium's 40.08, and nickel's 58.69. So what we can now say is we can say a nickel atom is 58.69 over 40.008, which turns out to be 1.464 times as heavy as a calcium atom. See, all we did is we just put the mass of the nickel over the calcium. All right, it is 58.69 over 10.81, or 5.429. No, there's four significant figures there. 4.29 times as heavy as a boron atom. See, so now I can start comparing masses of atoms to atoms now that I've got this relative mass unit. You've got a nitrogen atom here, which weighs 14. You have a hydrogen atom, which weighs 1. How much heavier is a nitrogen atom than a hydrogen atom? Well, it's about 14 times heavier. How many hydrogen atoms would it take to equal the mass of just one nitrogen atom? Well, it'd take 14 of them. Can you find an element in the periodic table that is twice as heavy as a nitrogen? Well, how about silicon, which weighs 28? See, so now you can start comparing masses of atoms with atoms, other atoms in the periodic table. Now that you know something about atomic mass. All right. Now, if you look in the periodic table, what is the mass of carbon? Well, it's 12.01. 12.01? I thought it was supposed to be exactly 12. Where'd the 0.01 come from? Well, maybe that's where we'll pick up in our next video. So we'll quit there for now. We'll talk about that particular problem. And I'll show you how to calculate the atomic mass of anything in the periodic table. And we'll show you where the decimal comes from. So good place to stop there, and I guess bye for now.